Hello and welcome everyone. So if you see what we have been discussing in the previous sessions, we saw gradient descent, we saw a lot of stuff. So one thing was constant. I'll again remind you that the thing that we start with was data. So we had data that we wanted to feed into our model, and we wanted our model to train somehow. So this data was like this, xi, yi, and we had some n samples. Okay, this class is probably going to be one of the most important classes from a mathematical perspective, so that once you see these equations and you're no more scared. Okay, so we have data. So what is data? Basically, data contains information. So it contains information. Okay, after that, what we have to do is we have model. So because you know what mathematically model is nothing but a function. It's a complex function. So you give some input to it and it learns that. Okay, that is model, and model has to learn something. So what is the meaning of learning? Learning basically is to adjust these parameters, theta, which we have weights and biases. So you can write it like this: you have theta, you have a lot of weights, and you have biases associated with those, and this you have to learn. And then you have an objective function. You have an objective or cost function, or you call it a loss function, call it an error function. There are a lot of names for it. Okay, they're used in different contexts. Okay, you have a function by the help of which, there's one thing that we have seen mean square error. Suppose you have some function based on which you are making prediction. Okay, this is the actual value. Okay, and then square it up, and let's suppose you do it over all the data points from 1 to n. Okay, and then you average it. You see what is the average error that I have. So now this is the machine learning setting that we were discussing. The first thing is we should somehow know about data. So we'll have a deep discussion on data. Okay, because there are different types of data that you should have. Sometimes you have to deal with speech. Sometimes you have to deal with images. Sometimes you have to deal with videos. Sometimes you have to deal with text. There are a lot of types of data which you have to deal with. So we should know how to sort of encode this data. Okay, so we'll have a discussion on how to encode speech data, how to encode image data, what are different techniques, how to encode text data, video data, or sometimes you have multimodal data. So where you have data which can be speech plus video, or which can be, let's suppose, speech plus say some other dimension, let's suppose text. Sometimes you can have image plus text, and a lot of things can be there. You can have multimodal data as well. Because as I said, machines only understand numbers. They don't understand anything except numbers, or rather binary. So all the data should be given in numbers. So we'll have a detailed discussion on all of these. And the second thing is models. Okay, and we have to learn a lot of models. And then there comes the learning, how to have this learning algorithm, because we saw one algorithm, gradient descent. And then we'll have to see these objective functions. So today we'll start our discussion with this objective function. Okay, so we'll start our discussions on this. So as I told you this, so you have this function that you want to learn. So now let me plot a simple graph. Let's suppose this is, ask me as many questions as possible. Okay, suppose this is the real function that you want to learn. Okay, this is the real function. Call this, suppose, some f of x. So this is the real function that you want to learn. And now what you are learning is, call this g of x rather, because I have used f of x. So now you are using your model. So that model is represented by f of x, but it's a parameterized model or a parameterized function. So it's parameterized by w. W is these weights and biases. I can collect them in one matrix that I can just call that w. So w are these parameters, or I can call this theta also. Okay, let me stick with this w notation for now. So this is my parametric function that I want to learn. Say the model learns this function. So this function over here, something of this sort. So this is f of x w. So this is the model which model learns. Now if you see this, so this orange portion that you see over here, this is area between two curves. Okay, one curve is the curve, or the one function is the function which is the actual function there, the g of x. This is the function that is the generating process. Whenever you have data, so this comes from this probability distribution, and there is a function associated with that. That is the g of x. And then you are trying to approximate that function. You are trying to model that function by using a neural network, and that function is approximated by f x w. That means it is parameterized with w, and it takes input x. And now you see this is the error, because I want to have a discussion on this cost function or objective function. Okay, everybody clear on this? So this is the error that we want to have. So this is the error. So can anybody tell me the idea? How can I quantify this error? Can anybody tell me how can I quantify this error? I'll give you maybe a minute or so. How can we quantify this? Yes, please. The answer given was that we have to use integral. Okay, so we have to compute the total error. So how can we compute total error? Total error somehow have to be computed by using function. We have to find this area between these. Okay, and we have to minimize the error. The total error because this takes w as an input. So we have to compute the total error. So it will be integral of, let's suppose, from minus infinity to infinity, because this function can be defined on this. And we have to define a function. Let's call that a divergence function, some function which will quantify this error. So this function will take two other functions as input. So it will take this f of x and w and comma this g of x and then dx. Okay, so it is taking both. So what Fahal said is that we can put minus. So that is, you are giving an example of a function. So what I said is, this is the conceptual thing first. So here you have to have a function which will take input as these two functions. Okay, and then it will somehow quantify this error. So how many of you understood this point and agree on this point? So we have to come up with a function, this divergence function. So it will see, okay, it will basically quantify that error, and that will be some function. As one instance, you can put a minus in here. Okay, you can just subtract these two things. But this is very important. You have to understand this. So this is what is our thing. Total error is this, and you want to come up with, you want to minimize this error. You want to find such w, okay, which we'll call w star. So that I'll write this argmin of this. So argmin, let's call this function as total error. Argmin of this function, total error of w. So this is your objective. Okay, this is the objective function. Okay, the total error can be computed by this. You have to integrate from minus infinity, because this is area under two curves, and two curves are this f of x and g of x. And now you want to find a function. You want to find a function which somehow, if I give input this and this function, and it will tell me how much off are they from each other. Okay, and this divergence should have some properties. So if f of x, w, and this g of x is equal, so it should be giving me equals 0. So I want some properties. This divergence function should have some properties. Give me a second. I'll just, now I defined this divergence function. So what are the properties that divergence function should have? So I'm saying that this divergence function of f, it will take this f of x and parameterized by w and this g of x. So this is the true function. This is the parameterized function that the model is learning. So it should be equal to 0. When should it be equal to 0? If f of x, w is equal to g of x, if it exactly models that function. So it should be equal to 0. Otherwise, what should happen? This divergence of f of x, w, comma g of x, it should be greater than 0 if it is not equal. If x, w is not equal to g of x. This is the property that I want my function to have. Why this property? Because I am somehow trying to estimate the loss. I am somehow trying to see how much off is this. So I want this error to be positive. This error is positive. It means there is some error. So our model is not purely estimating, or 100% it's not modeling this. There will be some error. Okay. And if it is equal, if our model is exactly giving the same function that we wanted, that was there in the generating process, then it should be equal. So these should be the properties followed by this divergence function, followed by this objective function. Everybody on the same page for now? Okay, the question asked was, will it be a single number? Yes, it will be a scalar. It will be a single number giving you this. So if you are having a number positive, let's suppose 20, so this is telling you that you have an error of 20. Suppose you have a divergence of 20 somehow. This is quantifying how much off you are. So if you did something to the network, if you adjusted weights and bias and you went to, let's suppose 18, it means, oh, you did some right things. That's why your error, or what I can say is difference between these two distributions, difference between these two functions got decreased. So if you again suddenly did something and it went to 30, say, okay, then you messed up something, because now your difference of these functions is quite high. Okay, this divergence is quite high. Okay, this will be a single number. Now this is the property I want. Now there are big two problems. Okay, I'll tell you what two problems there are. So this assumes that input, basically we have some inputs and we should know this g of x, but in reality you know that you don't know this g of x. So we do not know g of x. We do not know g of x. This is one problem. If we do not know g of x, okay, so what do we know then? We just have samples, we can sample from this function only. We can sample from this. Okay, if we have a function, if you are given input output pairs or some data from that generating function, you only have access to the samples. So you can think it as we are sampling from that function. When you have this data, you have basically samples from that function. That is the only access you have. Okay, now we'll go to the probabilistic things. Okay, we'll now go to probability. You will see that how probability is getting used. Now basically we cannot compute this. So if you cannot compute this integral, so total error, you cannot compute this. So what you can do is, you had integral of this divergence function, and then you had this input function. Okay, this is what you had. Now if you cannot access this function, so what you should do is now, so you should somehow have the probability distribution then. Okay, if you do not have access to all of these, you can still create probability. You do not have this g of x, but you can represent this g of x in terms of probability. Okay, so you can represent somehow that in terms of if you represent that in terms of probability. Okay, what will happen because of that is once you represent that in terms of probability, you can bring it into the expectation world. Okay, so I'll write that thing. So you know that I can, and you know the definition of expectation. I don't need to go there. Expectation basically when we read about random variables. So there we saw that if you have a discrete random variable, you will take summation of the random variable xi, the value it takes, then probability of xi. Okay, and then you sum it over all these things. This was the expectation. I'll not go there again. So now what you can do is you now have access to samples. So you will say that I cannot compute the integral of this. So what I should do is I should compute expectation of this then, because actually this can be converted into summation. Okay, realistically by using let's suppose you cannot integrate over all the things, so you have to use an expectation. So you will say this expectation x was drawn from this probability p of x. Okay, there will be some probability distribution of the generic function. You have g of x. G of x is the function. Okay, this function will have some probability distribution called that p of x. Okay, this x is drawn from that. If a sample is drawn from that. So now how we can represent this? So you can represent this divergence function like this. This divergence, you are basically now computing expectation. You cannot integrate over all these things because you only have access to the samples. So this is how you can write it. Not computing this, rather computing the expectation. And now you can in turn again write it in terms of integral. So if you go back, so if you equate this, so this will be integral of divergence of f of x w, these two functions, and then the probability of x. This is how expectation is being written. Okay, you have some value and multiply it by that probability. This is how we write expectation, because as I said, this thing can be converted into the expectation. Okay, and this is one problem. So the first problem was we do not have access to the g of x, so we only have samples, so you cannot compute this, rather you can compute the expectation. So this is what we can compute. Look at our second problem. The second problem that we have is outputs can be random. Outputs can be random. So what do I mean by that? By that I mean, if let's suppose we have some input x, it could yield two different labels. It can have one label y1 and y2 sometimes. The same data point can yield two different labels because of noise. Because you know in real process, in real data, you sometimes have noise, and sometimes the same data point can have two labels. Okay, once you give that data point, due to noise it gave label y1, and at the time it gave y2. So this is outputs are random. The first thing was we do not have, this was the first thing, we do not have no g of x. The second thing was outputs can be random. Again, if output, again you should not then use this g of x. So what you should do, you should use corresponding labels then. So what I'll say is, now you are taking this expectation x comma y. Now this is taken from probability distribution of x comma y. Initially we just were taking probability of x. We had a distribution g of x, and we were taking these, we're sampling this x from the probability distribution of x. Now we're taking joint probability of x and y. These are two things, and then we're sampling x comma y from there. Okay, now we'll also replace this g of x, because g of x, and we don't know its probability altogether, like, because y's can be random. So again, expectation of this, and we'll say divergence of f of x w comma yi. Okay, because this is the axis that we have, and this is called, this thing over here is what we can derive. Okay, this can be done, this can be done. The first problem we had, we did not have access to g of x. So what do? We said, okay, we'll sample from that distribution that points x. Then we said, oh, we have problem with labels as well, because sometimes there will be an issue that one data point due to noise can be having multiple labels. Sometimes it will give one label, the same data point, because of the noise. So we again changed this. So now what is the best possible thing in theory? So what we can do is, we have to minimize this. Let's call this thing as R of W. R of W. Okay, so this is called as Bayes optimal predictor. Okay, or we also call this as empirical error. Empirical error, because this is not real, this is empirical, because you are seeing it from data. So what you have to do is, you have to find W star such that you minimize this expression over here, over W. R of W should be minimum. So this over here is your objective, new objective. This is your objective. Okay, why can't we do it directly? Again, P of this is not accessible. G of x is not accessible. And second thing is, we do not have access to y, because it can be random. So this is called as empirical risk. Okay, so this thing over here that you saw is called as empirical risk or empirical error. So we can write it empirical risk, and this is our objective, and this is called as empirical risk minimization. So we have to minimize this. Okay, we have to empirically minimize this risk. How many of you are on the same page till now? Okay, well, now we know that, okay, we can do this. Okay, well, now we have to have a discussion on this divergence function. Somehow we should be able to know this divergence function now. Now we know that, okay, we cannot have access to this. So this is what we want to minimize. Now moving on to the next discussion. Now we'll go to a bit of information theory, then I'll come back. Okay, before discussing all of these, we'll go to information theory, and then we'll come back and we'll define this. So now we can call this a loss function. This usually is called loss. Okay, and this is not the right word to use because, as I said, it's called empirical risk. Sometimes you might have heard about loss, so this is also considered loss. Okay, sometimes you have heard about cost. What is the difference between cost and loss? So you sometimes also add regularization terms. You regularize the value, then you call that cost function. Loss is basically defined for 1 point or for 1 point without regularization. Sometimes you define cost as well. Cost is overall cost. Then you also add regularization, and then we'll differentiate this maybe in the later classes. But here you have to know that actually this is the empirical risk. Okay, and this is the best we have. Okay, and does it guarantee that it will model the functions exactly? No. Why? Because we are sampling. We don't know how good our samples are. Are our sampling representative of our distribution? Are the samples good enough that they are representing the function that we are trying to model? So it depends on all. That's why it's called empirical risk. Now we have to have discussion on some information theory. Okay, and then we'll come up with how to construct these divergence functions. Okay, you might have heard about like we have binary decision, binary, let's suppose, loss. And then you might have heard about cross-entropy loss. You might have heard about KL divergence. So all of these come from this. So first we will have some discussion on information theory. Okay, now to understand this, as I said, data contains information. Okay, that is the base assumption we have. Data, whenever you sample from some distribution, so you assume that you are unveiling the distribution. You think it like this. You see it from the probabilistic lens. You have an urn which contains balls. Okay, let's suppose it contains red, green, blue, some 3 types of balls. And this urn is totally sealed. You don't know what is inside that. Okay, you don't know what is the distribution because you know about distributions now. So say you have 30 red balls, you have 20 green balls, you have 10 blue balls. That is inside it. But when you sample it, when you give it a real good shuffle, and then you can basically only sample from it because this thing is hidden from you. Okay, and because it follows the distribution. There is a real distribution in it. So whenever you sample a ball, okay, whenever you know that if it is a red ball, blue ball, you are getting some information and that is helping you to estimate the distribution. Okay, that's what basically we are doing. So whenever you see a data point, there is some generating underlying process, there is some probability distribution. You do not know that. You have no access to that. If you had access, no point in machine learning, no point in doing deep learning. But we assume that nature is doing something and there is a generating process for that. So whenever you see something, whenever you observe something, that means it is giving you some information. So what is information now? So information is actually degree of surprisal. So it is degree of surprisal. So what I mean by that? So let's suppose if I tell you tomorrow you will see sun rising from east. I say this. So there is nothing surprise in it. It is not adding anything to your information. If I say, let's suppose we will have class tomorrow, not much surprising because we have been having classes. So it is not like that surprising to you. It is not adding that many information. So when is information happening? So when are you basically adding information into your database, or when are you getting knowledgeable? When you are feeling something surprise, when you are feeling, oh, there is some surprise in this. So if I can somehow quantify this degree of surprise, you see, I'm again bringing the theory and then I'm telling you, first I said data contains information. Now I have to quantify, okay, what is the meaning of information? So how do you say that this data has information, this doesn't have information? So I'm saying that you should somehow be surprised when you see that. If you are not surprised, that means it has not added anything to your information. Then you are okay with that. As I give an example, if I say that today after let's suppose 7 p.m. you will not see sun, pretty okay enough. Why? Because it will be night time. I won't be surprised. Okay. Now I have to quantify this. Basically, I want to see what do I mean by information. Okay. As I said, vaguely speaking, information is the degree of surprise. Okay. How much surprised will I be? Now I'll have to quantify this. Okay, if I will be surprised, so how can I quantify this? Now I'll bring into the mathematics again. So how many of you agree that information is how much degree of surprise is there in the information is in that data point? Okay, now we'll bring in that. Okay, now we'll see that. Let's suppose we can again bring probability. You see how powerful probability is. If some event is very low in probability, if there is an event which has very low probability of happening, and it happened, you'll be surprised. Okay, if you are surprised, that means it contains information. It contains more information. That means somehow this information I can say information, if I have some message X, information X is inversely proportional to probability. So what is the meaning of this? So I am now trying to quantify this degree of surprise. I am saying if you are seeing data point and if it had very less probability, say it had probability of 0.1 and it occurred, oh, you'll be surprised. Oh, this event was very unlikely, but it happened. So it gave me a more degree of surprise. So it adds to my information. So when I said that tomorrow you will see sun rising from the east, it almost was 0.99 probability was there. So there was very high probability. That means there was very less information. So more probability, less information. That's why I'm saying there is some inverse relationship. Okay, if you see that some event has very low probability, that means it contains more information. If it happened, it will increase the information more. It will give you more information content to that. So now this is proportional. Now I somehow have to bring a function which will behave like this. Okay, now if I say this, if I say two events are there, I have event A and I have event B. So these two events, if they are, let's suppose, mutually exclusive events, okay, or I can say that these, rather than mutually exclusive events, I should say independent. I am rather confusing you people. So if they are independent events, so we have seen what are the independent events. If happening of A gives no information about B, happening of B gives no information about A. So if something, if P of A happened, my probability about B is not shifting. I am not doing any update to B because it is equivalent to that. That is how, but that's the meaning of independent events. So now I have to have a function of this. So if I take this function, if I take this function of probability of this X, okay, this function of probability of X, so somehow I should be quantifying this. I need such a function which will follow this. So probability of, if I have now P of X, if I write f of P of A and P of B, say f of probability of A and B, so this should be somehow equal to f, a function of P of A plus P of B plus function of P of B. Okay, I will not discuss probability here because we have discussed in detail. Now you can say probability of P of A multiplied by P of B. This is the meaning of independence. This is probability of P of A plus P of B plus f of P of B. So I need to find such a function, so which will sort of behave like this. Okay, if you see one function which behaves like this, that's log function, because that function is log function. Okay, I was telling you that information of X is inversely proportional to 1 divided by probability of that event X. Now what I said is, instead of this, it means that there will be some function. If I give this input, that should give me the information it has. So suppose I of X, it should be equal to some function of this P of X. Okay, I basically want to remove this proportionality. I said there is a property. If it is in terms of probability, so that should somehow, a function should behave like this. So what is that function? That function is log function. So I can apply log onto this. So I'll say information of X is equal to function log of, let's say 1 by P of X, because it's inversely proportional. Okay, so this is 1 by P of X, and you know information of X, this is equal to minus log of P of X. The thing that you see over here, okay, this point over here, so this is your information content. Everybody agreeing on this point? So how many of you are understanding this? So this over here, the thing that you are seeing over here, so if you are giving me, let's suppose a point, if you are giving me, let's suppose some instance X, and I am applying this log, so I am telling you what is the information content in that. So this is the information content by using the log. Any questions till here? Now you saw that this thing over here is, we can say that this is information, how much information is there. Okay, now we have to define term entropy. Okay, entropy in terms of computer science. Now how is entropy defined? So what you can do is, if you have this probability distribution, now because you know we have a distribution, say you have some distribution, you have distribution P and you have some other distribution Q. So this P and Q, in terms of our distribution, you had this function G and the real function G of X, and then you had this f of X W, basically the estimating one. Suppose you have 4 classes. You have class, say class dog, cat, say bus, and cycles. These are the class images that were given to you, and now you know that they will follow some probability distribution. Okay, this probability distribution is there. Let's suppose in those images, if you know the real sample, the dog is occurring 0.4 times, suppose 0.25 times, 0.15 times, and 0.2 times. So this is the probability distribution, and you are trying to estimate this. Okay, you want to estimate this probability. Or in the similar fashion, you, let's suppose, are now given one image, and you are given one image. You are saying, okay, I have seen the data set. So let's suppose that image was actually of the cat. Okay, so the vector should have been like this 0, 1, 0, 0. So all the probability should be given to this. So when you are estimating that, but you will predict something. You will predict, let's suppose with 0.4 probability it is a cat, with 0.2 and 0.2, so this is the probability, and you are giving some slight higher probability to this, because you don't know this probability, and there is some underlying probability towards this. So what you now do is, so you have probability and you have that point also, so you have the information content in that. You have log of p of, let's suppose, xi. So if I write it like this, so this is the information content, I can say. So if I just multiply it with that, so I'll say log of this, I can say x takes value, so this is a random variable x, it takes value xi minus of this, so this gives you the information content. So if you just multiply it with the probability of that, if you say probability of x is equal to xi, and you keep this minus over here, so this is how entropy is defined. So this is defined as entropy, and if you sum it over all the things, you sum it over xi goes from 1 to n, how many ever the variables were there, so this over here is called as entropy. So what you can see, entropy is basically expectation. Okay, this is the expectation. What do you expect? Okay, as I was telling you that we were showing you the example of number of bits being used. Okay, and I did not record that though. So, but you got the point here. So, what is entropy? The entropy basically is defined expectation. How do you define expectation in terms of random variable? If you have a random variable x, it takes values, say a, b, c, d. It takes these values, and they have probability 0.1, 0.3, 0.4, 0.2, some probability of this sort. Okay, so now you are being said, okay, what is the expectation of x? Okay, and we have read this about expectation. So expectation of s is summation of this x takes value I, probability x takes value xi multiplied by this value xi. Okay, and this goes from 1 to n. So our numbers are there, how many values this random variable takes. So this is called as expectation. So this entropy is basically this expectation. But here what you are doing is you are applying log onto this. So you see over here, it is like expectation, not exactly like expectation. You are taking this probability of this, and then you are taking the information content. So at average, how much information will you find there? So this is the probability of that, and this is at average how much information will be there. At average, very vaguely speaking, at average how much information will you find? Okay, you have to, if you do not understand this, then there is some problem with the expectation, and we have done a lot of things on expectation. I hope that this is clear for you people. Now this is giving me the expectation. It is like computing the probability, and this is like this is having that value. Like this is the value it takes. This is the information content, and this is the probability having that value. Okay, when you multiply these two things together, this is telling you at average what is the information content that you are expecting, and this is formally defined as entropy. So how many of you people are clear on entropy? What is entropy? Okay, today's lecture is getting a little math heavy, not that much. So what I'm trying to tell you here is this is how entropy is defined. So entropy basically is telling you, and sort of expectation. So but what is that expectation? It is basically giving you the information content. Okay, at average, what is the information content in that? So what is information? So I told you that information is the degree of surprisal. Okay, so degree of surprisal can be measured if the event has less probability, and if it occurred, that means it is giving you more information. Okay, it's inversely proportional to that. As we have to find a function which somehow gives me that. I want to remove this proportionality. I want to bring some function which will map this. So I said log is the easiest function which shows that behavior. So now if you see this log, so this I of x is equal to minus log of px is the information, the amount of information that is there in this data point x, or when that thing is sampled, or the sample x. Okay, now what I said is, I said if we have distribution, we have the distribution p, we have the distribution q, and we'll come to this distribution once we do these divergences. So this was the initial distribution that was actual there. So that why we had actually sampled the data points from. Now we want to define entropy. We want to say, okay, we are sampling points. Okay, what is the expectation? What can I expect? I said, okay, can you take this information, amount of information, and then you multiply it with the probability? What was the actual probability of that? So this is called as entropy. Okay, so this thing over here is called entropy. So what we are trying to understand basically these cost functions. Okay, we have to come up with these divergence functions. So as I said, by giving this information about information theory, you are now I think good enough to understand the cost functions or the loss functions. So we'll study about KL divergence. So we'll study about cross entropy loss. So we'll study about say mean square error that we have already studied, and we'll study about, I think these three are enough. So this is usually used for say regression problems, and this is usually used for classification problems. and I think maybe more than 80% of your deep learning will be either a regression problem or a classification problem. You'll have to classify things, or you will have to give some real value things. So this much information about information theory is enough to understand all of these KL divergence. So what is the meaning now? So what I have to do is, this divergence function should somehow tell me how different are these functions. So we have f of x parameterized by w and this g of x. Okay, now I said the problem is also that. So what you have to do is, you will have to somehow quantify. Okay, if I have one probability distribution, I'll have this p. So that is the real distribution, which we do not know. And then you have this q. Q is basically this one, the one you estimate. Okay, so this is the one we predict. Okay, how much off are they, or how much similar are they? What we were discussing in that, we were discussing how to quantify this information content. So how to quantify the information content? It was information content of any event x. We said that it is proportional to the inverse probability. It's proportional or inversely proportional to the probability of that event. Okay, then from this we came that information content, we derived it that it had some properties of this. We should have a function by the help of which we can remove this proportionality constant. We said that this is equal to minus log of x. Okay, this is how information content was defined previously. And now after that we also discuss what is entropy. We discuss about entropy a bit, because entropy can be seen by physicists in a different way, but in computer science we somehow relate this entropy with the information. So what was the definition of entropy? In a nutshell, it was expected surprise. I said that surprise somehow contains information. If you are more surprised on seeing an event, that means that information that you gain from that event is more. I gave an example that if let's suppose say we'll have the class tomorrow. So usually will have the class tomorrow. So that the probability of that event happening is very high. So that means there is not much information content with that. So when surprise is more, information is less. So that is what this proportionality constant. We said that we can say the degree of surprise can be quantified by probability. If an event is more likely to occur, the surprise in that is less and information content in that is less. And now we'll have to see what is the expected surprise, because we'll be seeing the world around us, and if we are observing a process, so every process can be mapped by the probability distribution. If you are seeing certain images, if you are seeing, let's suppose, certain audios, so all of these things which we have discussed in detail in functions and probability, that you can see these problems, like some generating function is there is some underlying distribution which is generating these data points. This entropy was now expected surprise. So if surprise is minus log of x, so I said if you have a probability distribution, consider let's suppose we have some random variable x, some discrete random variable x. So we can call, let's say, if it takes values, say x1, x2 till x, suppose n. So these are the values it takes. Okay. Now for all of these there will be probability. So probability x takes value x1. So this is how we write this. So we can write in general probability x takes value xi has some probability. Okay, and this probability can be also defined by probability mass function. So what was the expectation? The expectation that we defined, if you have to calculate the expectation of x. So we calculate it like this. You have this xi multiplied by probability x, this value x takes value xi, the probability mass function, and you sum it over all the data points. And this was how expectation was defined. Okay, and now in this case we are calculating expected surprise. So at average, what is the information content in that? So expected surprise or expected information content. And how to define that now? So we can say entropy, that is equal to, so the first thing that we have to see is this probability distribution. So we'll say xi, and the degree of surprise is log of xi. Okay, and we'll sum it over all the points. I takes value from 1 to n, and this negative quantity, because this is the degree of surprise is measured by minus log of xi. So this is how entropy is defined. Everybody clear till this point? Any questions? So let's now see this. Why this entropy? Why do we use this entropy? Like how does this measure some sort of information? So it should information should have some units. Okay, I had a brief discussion with you in the previous session, but I didn't record that. So now this entropy has some units. So what is the unit of entropy? The unit of entropy is either bits or nats. Bits or nats, depends on what is the base of log. So if the log is having base 2, the information that you measure is bits, and if it is having log to the base e, that is natural log, so you call this information content as nats. Okay, this is how we define the unit of this information entropy, because entropy information is usually, if you see this, so this is log x. So if you say log of log to the base e, you will say this much information content is there. So entropy and information content will have the same units. So let's suppose now if you take some sort of random variable x. So suppose you take a random variable x which can take 8 values. It can take some 8 values. It can take x1, x2 till x8. So these are the values it can take. Okay, now you know that if you have to see the information content in that, so you'll have to know that what is the probability distribution, what is the underlying probability distribution of this. So how is probability distribution defined? You have to give me the probability mass function for this, because if this is a discrete random variable, so consider this to be discrete random variable, so you'll have probability mass function associated with this. Consider this as uniform random variable, uniform discrete random variable, so each of this will have probability 1 by 8. Okay, all of these events will have probability 1 by 8. So now if you have to compute the information content in this, okay, so how do we compute the information content in this? This will be log, we'll here consider in bits now. So this is log of minus log of 2 and then 1 divided by 8. So each of this will have the probability for this event. If I have to compute only one event, so I'll take one event's probability 1 by 8 and then to the base log to the base 2, and then this will be equal to, I think, 3. So this is log 2 to the power minus 3, and this will be minus. So if you use the algebra of logarithms, so you will get the information content in this is 3 bits. Okay, so yesterday I had a discussion with somebody, so he went for the BARC interview. So he said they asked me a question, but I couldn't answer that question, and I don't know how to answer the question. The question that he was asked in BARC interview, he was asked that interviewer was there, he had 2 coins in his 2 hands, so he flipped both of these coins together, and then he said, what is the entropy of this? Can somebody answer that question for me now? So here there is a slight mistake. It's not just xi, it is probability of xi. Okay, probability of xi. And information content also, if you see over here, so this is log not event x, so this is probability of x. I think we were clear in the previous section about this, because we just have to apply log on this, log of this p of x. So I just wrote it as x. So now it's actually probability of x. So this is surprise. So now I said about what is the expected surprise or expected information content, that is this probability of xi, and given this value xi. So now this equation becomes, so this is the right equation now. So the question that was asked is, if we flip 2 coins together, so now on flipping 2 coins, what is the entropy of the system? So we assume that each of the toss is independent of other toss. So now we have total 4 possibilities. First thing is, we'll see that what is the value that this random variable can take. So this random variable can take these 4 values, and this is uniformly distributed. So how can you say that this uniformly distributed? Because events were independent and we are not given any information. So the best assumption that we can take is that this is uniform distribution. And now we are assigning probability to each of these. And on calculation, you can just say 1 by 4 log of 1 by 4, and you can add, you will get 2 bits. So one important question that was raised here is, if we just compute the information content of this event, say any of this. So if you take probability x is equal 1 by 4 for first event, so you can directly compute log of p of xi. So that means log of minus log of 1 divided by 4. So this also comes out to be 2. So information content is equal to entropy. Information content of x is equal to entropy of that distribution. So when it's a uniform distribution. Okay, let me first tell you the intuition. Why is it so? Okay, so entropy is like computing the average. Okay, let's suppose if you are 10 people in this class right now. So if each of you got 10 marks, let's suppose we took a test and marks were out of 15. So if each one of you got 10 marks, so if I say what is the class average, so you just can't speak to one person, okay, how many marks do you get in the class? How many marks do you get out of the test? He'll say I got 10 marks, but you know that all the people in the class, they got equal marks. Then you can directly say that the average is also 10. You don't need to ask each and every person that what are your marks and then compute the average, sum them out, divide by the number of, because you know that each of the people in this class got the same marks. Similarly in this probability distribution, so when I'm computing average, so I have to compute information content, and then there is entropy. Entropy is average information content. So if you compute information content in let's suppose one case, if you consider information content in let's suppose in this case where we have only this, because now the distribution is uniform, you need not to compute the average, because whatever you you have the value for one instance, the whole value is throughout, because it's a uniform distribution, or the probability for all the events is equal. So average is equal to whatever is for the one instance. So did you get the intuition? Pretty easy. Now you should not always rely on this. You should not always rely that if I compute an information content somehow and then I'll get the entropy. As I said, entropy is expected surprise, information content, or expectation is usually computed when you don't have the whole data, you have some distribution of the data, you are given some samples. I think we have a question. Yes, please. It was a very good question asked, that why do we measure it with bits? Okay, what does this size signify? If the information content is said 2 bits, so what's the meaning of this? So usually when we say something is 2 kilograms, so we have some base measurement, we have some reference point with which we refer to it. So in this case, we said that this entropy was it was invented, or it was discovered for communications. Okay, so when we have to communicate something, how much size will it occupy, how much bits will it occupy? So if it takes more space, or if it is of more size, that means it contains more information, loosely speaking. The example is that if you have some file in which there are a lot of repeating patterns, so because usually in computer science a file is nothing but a string of bits or a pattern of bits. So if you have 11011 something of this, or 000, a huge file of bits. So if there are a lot of repeating patterns in that, so you know that you can use Huffman encoding to compress this file. So you can compress the file. So when you are compressing the file, the size will be less. So you took some size which is a little greater. So when you compressed it, it will be less size. So you have some more size. So when you compressed it, you will get less size. But one thing is constant. The information content that was previously there is equal to information content at the final stage. So initial information content was equal to the final information content. So this Huffman coding, because you know that this is called as lossless compression. So why is it called lossless compression? Because you are not losing anything. Information content is still the same, but you are just saving some space. So as I said, size has something to do with information. So if you take more bits to store this information, that means it has more information than that. So that's why we use this information of bits. The more bits you use, that means probably after the compression, after it's a lossless compression, you can use maybe 1000 bits, but if you use some better encoding, so these are called encoding schemes, because you'll have to encode the information somehow. So if you're using better encoding, if you're using optimal encoding, so what is the meaning of optimal encoding? So optimal encoding means if you cannot use less than those number of bits. Okay, so in this case, I said that information content is 2, so you cannot use less than 2 bits to convey this information. If you have to send these 4 possibilities, okay, you have to use 2 bits. You cannot use less than that. Why can't you use less than that? Because it's the uniform probability distribution. So one more thing here. So entropy is highest in uniformly distributed distributions. So entropy is highest in uniform distributions. So when the data is uniformly distributed, entropy is highest. You cannot have less entropy in uniformly distributed, because each of this information content is equally likely occurring. Okay, but if there is some distribution, if there is skew distribution, if it's not uniform distribution, then maybe you can reduce the number of bits. So that's why I said optimal coding. So optimal coding basically means you cannot do better than this. If you use more bits, you can probably transmit the same information. The optimal encoding would be where you will use the least amount of bits that are needed to send or encode that information. So, and this is called lossless compression. You can do lossy compression as well. So where you lose some data. Many of the compressions that you do in images are lossy compressions. You have a PNG file, you convert it into JPG file, it's a lossy compression. You maybe do something, your image is 1 MB and you lose a lot of details in there, but it's not visible to human eye directly. And you can, in machine learning, you can do PCA, principal component analysis. That's also lossy compression, okay, because there also you lose something. So, but in Huffman encoding, it's a lossless compression. So when you do this lossless compression, so what you basically do is you keep the information content same. Information content initially is equal to information content at the final stage. But what you do is you have more size initially, but you have less size at the end. So that's why we consider this information content, we measure this information content or entropy in terms of bits. I hope now this is clear to everyone. Okay, now I was telling you that if it's not uniformly distributed. Okay, one more thing is that entropy is maximum for uniform distribution. Okay, why is it maximum? Because you saw that there is nowhere that you can use less number of bits. Let me take an example to make you understand this. Suppose we have a random variable x again. Say it takes some 8 states. It takes 8 states a, comma b, comma c till h. So these are 8 values it can take. Okay. Now I'll give you the probability distribution. I'll give you probability mass function because this is a discrete random variable. So discrete random variable. So I'll give you probability mass function. So probability mass function is like this. So probability that x takes value a, I'll directly write the values. I'll not write it one by one. So probability mass function goes like this. So 1 by 2, 1 by 4, 1 by 8, 1 by 16, 1 by 64, 1 by 64, 1 by 64, and 1 by 64. Okay, so this is the probability mass function that is given to this. Can somebody compute what is entropy of the system? Entropy of this. I'll give you maybe 2 minutes. You can use calculators. Let me do it. So if I have to compute the entropy of this, so what's the formula of entropy? If you go by the mechanical methods, the entropy is basically expected surprise, expected information content. So entropy, let me call that E. Entropy is E. That is equal to minus sum of all the observations that we have here, probability of x takes value xi, and log of probability x is equal to xi. So if you do this, so you'll be saying minus 1 by 2 log of 1 by 2. So if I just take this minus outside, keep it outside, plus 1 by 4 log of 1 by 4, and so on. I think this will be 4 times this. So 4 times 1 by 64 log of 1 by 64, something of this sort. So if you calculate this, so you will get 2 bits. So what's the meaning of this? The meaning of this is that you will require 2 bits to transmit this information, because if this is the information that you are sending these codes in the let's suppose you are sending these 8 things and you are repeatedly sending these 8 things. Okay, you can send, let's suppose this message can be hi, this can be hello, and something can be something else. So now if you see in the way that you are transmitting this information, now this x can take value 8 values, and but you know that this message has this distribution, it follows this distribution, or you are sending some 8 characters. In each message you are sending some 8 characters, and these characters are following this distribution. Now you can say that optimal encoding only uses 2 bits. So if you optimally use this, okay, let me show it. At average, let's suppose if you can say that if x is taking 8 values from, let's suppose, from a to h, so I can use 3 bits. Fair enough. But you know that this is not uniform distribution, so you can compress this file. So what you can do is, so you can only use 2 bits. How can you do that? At average you can use 2 bits, not just 2 bits. So for a you can use 0. Okay, if you see, the more probability used with less bits for that. That's how you are bringing the expectation down. Okay, because this a is occurring a lot of times, because it has 1 by 2 probability, 0.5 times probability, and it has 1 by 4, 1 by 8. So you give more bits to those which are less likely, and you give less bits to those which are more likely. Okay, a is more probable, so you will only give it 1 bit, and this is 1 bit. And then if you see b, now you will give it 2 bits. You'll say you'll encode it with 1 0. For c, you'll encode it with 1 1 0. For D, we'll encode it with 1 1 1 0, 4 bits. For E, maybe 5 bits. 1 1 1 0 0, maybe 6 6. And then for others also you will give 6. A B C D E F G and H. So you'll give it 6 bits for these, but different combination of 6 bits. Now if you see at average, how many bits are you using? At average, you will come that you are using 2 bits. So here 1, so this is 1, this is 2, this is 3, this is 4, and then 6 and 6. Something you could have used 5 bits, but again you will have to use some 6 bits, something of this sort. So now total, if you compute the average of this, so you will get 2 bits at average. That's what you do in half-man encoding as well. So if some message is frequently occurring, if there is a pattern which is repeating, so you give it less number of bits. That's what we did over here. So the information content in this case is 2. Okay, one more thing is that uniform distribution always has the maximum number of maximum entropy over here, and all the other distributions have less entropy than uniform distribution. Everybody clear on this point? Okay, if you see this, why this discussion? So this discussion actually was a detour, because we were trying to see that divergence function. So if somebody remembers that we said that, okay, we have to somehow find the optimal function. So if you we have to do empirical risk minimization. Empirical risk minimization, that's what we were doing. This is what we were doing. For that we read a bit of information theory, in which we read about entropy, and then we'll use this in cross entropy and stuff like that.